So far we have discussed primary and secondary primary steel making and ladle metallurgy steel making, and we have seen that how decarbonization, to what extent decarbonization is carried out in primary steel making vessel, and the quality of steel is maneuvered to the desired level through ladle metallurgy steel making. So, at the end of ladle metallurgy steel making, or an extensive set of ladle metallurgy steel making operations, so we can expect that the composition and cleanliness of steel are up to the satisfactory level, which meets the requirement of the customer. Now, we have to address two other processes or the subsequent processes, and these are basically the transfer operations and the conversion process. Transfer process and conversion process. Conversion means, because we will not be supplying liquid steel to the customer, we have to convert it to a solidified product. And when I left you last time, and I was talking about the transfer processes, and I was showing you that how molten steel is transferred from a ladle through. So, we have a ladle well here, and this is the refractory line ladle, and I showed you that we have a slide gate plate here. Okay. And then we have a collector nozzle onto which a ladle shroud is mounted. Okay. And that is what it is. And the ladle is physically covered. Okay. There is no argon bubbling now, and we have a free surface of the ladle, okay, and we have a slag layer sitting at the top, and the molten metal is being drained through the bottom. That is the typical scenario, okay, and that is what we were talking about. And the basic objective is that if you do not have this ladle shroud, okay, in that case what is going to happen, the molten metal will flow like a open jet. This is called a free jet in fluid mechanics literature, okay, and this is susceptible to huge temperature loss as well as reoxidation due to the entrainment of surrounding oxygen from the atmosphere. Okay. So, the ladle shroud basically allows us to team steel or transfer steel from ladle, okay, to a vessel which is downstream. So, the metal where it is going now, it is going to a tundish, for example, and this is at the first you can regard it as a buffer vessel which allows us to distribute molten metal into many molds which are downstream, and this we will discuss. These are molds, and this is a continuous casting setup which we call as a ladle tundish mold setup. So, this is basically a buffer vessel, you can, and this is tundish, this is our ladle. These shrouds, for example, so as I indicated that there is a collector nozzle here, there is a collector nozzle onto which the shroud is mounted, and the collector nozzle diameters typically, hole diameter typically is 40 mm to about 70 mm, that is the range, and the shroud diameter varies from about, I would say, 70 to about 165 mm. That is the shroud diameter, ladle shroud dia, and this is the collector nozzle dia. They depend on what kind of products we are making through continuous casting. Nowhere in the setup, as you would note, molten metal is exposed to the environment. Okay? That is why the Ladle shroud has been used, but yesterday I have mentioned to you that because it is a cup and cone joint between the collector nozzle and the Ladle shroud. Okay? So, this is our collector nozzle and this is our Ladle shroud wall, and so there is a mechanical joint through which because you are flowing molten metal, at what rate the molten metal could be coming out from tundish at a rate of nearly 1 ton per minute to about 8 tons per minute, depending on the scenario that we have. Okay? So, if we have 2 slab casting molds or 2 a thin slab casting mold, 1 thin slab casting mold or 2 slab casting molds, in that case the casting rate or the throughput rate could be 8 tons per minute under steady state condition. I will tell you later on what does that steady state condition implies, and in smaller section castings which we call as a bloom casting. So, blooms, again I will distinguish these products, and this is possibly for slab casting. So, that is the rate at which molten metal, if we cannot afford to drain molten metal at a too large a speed, because that is what is going to, first is it is going to erode the nozzles here, okay, and secondly it is going to induce a huge amount of turbulence in the jet impact region here. So, there is a limit to which we can really transfer molten metal from ladle. The slide gate will allow us to control the flow rate because the head is going down, okay, as a function of time. So, the slide gate aperture can be controlled, and as a result of which flow can be very high or flow can be very low, or the flow from the ladle and tundish can be matched. Okay. The outflow from here through the strands, these are called the strands. Net outflow through the Q1 plus Q2, net outflow through the strand is equal to the net inflow, then the tundish we say is going to be operated under steady inflow condition and steady flow conditions, and in that case what we are going to see? We are going to see a constant bath depth as a function of time. So, the air can get in depending on how perfect the sealing is, and as I have indicated that the sealing between the collector nozzle and ladle shroud is rarely foolproof. So, therefore, some amount of air ingression is going to take place. So, at that rate when molten metal comes out, locally in this particular region which is exposed to atmosphere through the leakages, low pressure regions thus created will draw. So, the pressure here is low because of the flowing of the fluid, but so if there is a leakage here, automatically the air will get sucked in from that environment, and that will lead to some kind of a scenario like we can have bubbles of air distributed. That is one scenario at low air aspiration rate, or this phenomena of atmospheric air getting into the shroud during the transfer process is termed in the literature as air ingression. Okay? And this air ingression needs to be stopped at any cost to the extent possible if we want to produce quality steel, because the oxygen thus ingressed into molten steel, which is virtually killed. So, steel will make steel susceptible to oxidation, and this contains now dissolved aluminum, which is just waiting for every opportunity to react with oxygen, and a little bit of oxygen going into the melt can really lead to significant amount of reoxidation, and that needs to be prevented at any cost or minimized to the extent possible. If you have, so this is a scenario when you have, and yesterday I have said that if the joint is perfect, hypothetically speaking, in that case this tube is going to be, when it is submerged, and this is also liquid steel, okay, tundish liquid steel, when the tip is submerged below the liquid in tundish, in that case the tube can be expected, or the shroud can be expected to be completely filled with liquid. It is a homogeneous flow of liquid steel through the tube. On the other hand, this sort of bubbles will be visible when air ingression rate is going to be small, and on the other hand what we can see is, for example, if you consider this, okay, and then we can see that molten metal can come something like this. So, it can come something like this, and then that is the kind of a scenario. So, we can, this is a severe air aspiration rate, where we can see that molten metal, has entrained a little bit, quite a bit of gas, and this empty space is the gas between the white line and the red line, okay. And this is a jet which is a severely constrained jet, okay, and this is a free jet. Free jet, it is not in touch with the wall, okay, but it is a severely constrained free jet. Earlier case, when we are talking about the metal being issued into an atmosphere, it is a totally free jet, okay. But in this case, because there is a wall, we will call it as a constrained jet, and this, because the diameter of this jet to the containment is very small. So, this is called a severely constrained jet. It is not a free jet, it is not exposed to the atmosphere. So, that is the kind of a scenario one can, but there is no way to visualize this really, in a high temperature scenario. So, the amount of nitrogen in tundish vis-a-vis the amount of nitrogen in the ladle possibly will give you to imagine that what kind of a scenario is there. If nitrogen absorption, for example, nitrogen in ladle and nitrogen in tundish, if you find that the difference is about 2 ppm or so, you can assume that there are bubbles like scenario within the shroud. On the other hand, if that difference is going to be something like 20-30 ppm of nitrogen, then you can think that the scenario is more akin to this kind of a situation. But nonetheless, what is important is any increase in nitrogen is a essential indication that molten metal has come in contact with the atmosphere. So, therefore, some oxygen must have, along with nitrogen, gone into molten steel, and that will lead to reoxidation of molten metal in tundish. If you do a simple macroscopic analysis, you can find out that how much of, so if you take a control volume, for example, and you know that heat is being lost through the shroud wall, and if you do a simple analysis, then you have a mass flow rate and mass flow rate going out here. So, you can say that m dot Cp, I will write with a mass flow rate multiplied by Cp, and then we can say the delta T, where delta T represents the drop in temperature between section 1 and section 2, okay, and that is going to be equal to the Q times, that is the steady state energy balance. And what is that Q? That A is equal to the shroud surface, which is equal to 2 pi RL. It is of course not so simple, it is not one homogeneous heat flux, because you can see that one part of the shroud is going to be exposed to the environment, the other part of the shroud is submerged, and this, the tundish may be covered also. So, one part of the tundish is, the shroud is going to be inside the tundish, and of that part, one part is exposed to the tundish atmosphere, the other part is submerged in molten metal. So, therefore, the shroud of the shroud surface is exposed to different kind of a thermal environment, but if you ignore this for the time being and you assume that a constant temperature prevails at the shroud surface, which may be based on measurements, and you can see that these shroud temperatures could be somewhere around 1200 Kelvin. So, you should be able to calculate that what is the radiation flux, convection flux is going to be less important, and therefore, if you know the emissivity of the refractory surfaces, and these shrouds are made out of mostly magnesia and alumina, they are the kind of refractories that we have. We also have a lot of carbon in it. They look black, and that is why I think most likely in industry, ladle shrouds, then tundish furniture, etc., nozzles, they are categorized as black refractories. Possibly they contain graphites to ensure that there is a good flowability of molten steel over it, there is not much wettability. So, and the composition of the shroud refractory, as I have indicated, is again is a highly basic, which has a large resistance to heat flow. It is good insulator, and the industrial terminology, while we say that the ladles are lined with bricks, these are not out of brick refractories, okay? These are black refractories, they are prefabricated structures and so on and so forth. So, if you take A is equal to 2 pi R L, which R is the radius of the external radius of the shroud and L is the length of the shroud. If you know the mass flow rate, if you know the specific heat, you should be able to calculate the delta T drop, and one can do this simple analysis to find out that the drop in molten metal temperature from shroud tip is approximately of the order of 2 degree or so. A similar approach can be taken in order to find out that what is the heat loss during the holding period. For example, if you know the ladle surface temperature. Okay? So, if you know the surface temperature, you can calculate the radiation heat fluxes, and then you can find a lump parameter approach like this, and you can say that you can write m dot, not m dot, mCp, rate of temperature drop of molten steel, and that is equal to summation of Q into A. I have written summation of Q into A because there are different surfaces. This surface will have one kind of a boundary condition, this surface will have one other different kind of one kind of a heat loss, this surface will have another kind of heat loss, and the bottom possibly will have another kind of a heat loss. So, therefore, Q's are specific to the surfaces, as I have indicated, that if you have a thin slack cover, no tundish physical cover, then the surface heat flux could be of the order of 100 kilowatt per meter square. On the other hand, through the little side walls, you can have 5 to 10 kilowatt per meter. So, you can also predict that how during the holding period as the ladle is sitting, and this ladle could be, as I indicate, that if you take 8 tons per minute and the ladles could be about 150 ton, okay, if it is 150 ton, then therefore 8 tons per minute will essentially tell you that roughly about 20 minutes or so. On the other hand, if you have a 60 ton ladle and if you are casting at 1 ton per minute a bloom, it can go for 60 minutes or so also. Okay? So, that for that long it is going to be sitting like this. So, there is going to be a change in the molten temperature. So, the first metal which flows out from tundish and the last metal which flows out, they are not at the same temperature, okay, and that creates problem, okay, sometimes in the tundish and in the subsequent mold, okay, and this is precisely because of the more amount of holding period and so on and so forth. So, one can predict also the simple analysis one can do and find out that what is the kind of temperature drop in the shroud which is not significant. Okay? But more importantly, if it is 1 ton per minute and it is sitting for 60 minutes, it is a small ladle, then you can have 20-25 degrees difference in temperature, and the viscosity of melt in the tundish is going to be as a result. The last metal is going to be more viscous, resistance to flow, it will be resistant to flow, because its temperature is smaller and so on. So, there are many associated problems associated with that. So, that is why we would like to use always, even the ladle is sitting on the turret, the draining is taking place, emptying of the ladle is taking place, or timming of the ladle is taking place. We are transferring molten metal from ladle to tundish via shroud. The tundish needs to be covered all the time, and so is tundish needs, ladle needs to be covered always, and so as the tundish, because we do not want. And today in the we must understand that in steel industries we get raw materials at room temperature, iron ore, scrap. During the process we take them to 1600 degrees centigrade, which involves heating process, and then once melting etc. is over, we convert them into solid products and bring them to room temperature to supply it to the customer. During this process, when the heat is lost, that 1600 degree to room temperature, what happens to the heat? Okay? When 20-30 years back, nobody was thinking about the recovery of heat, and today recovery of heat and minimization of heat loss is a very important. So, the more heat you are able to conserve here, the less amount of electrical power you will be needing in the electric arc furnace, okay? And therefore, those power where from they come from mostly these days in India, for example, from the thermal power plants and so on and so forth. So, therefore, this will have a direct impact on electricity consumption, on carbon footprint, etc. So, there is quite a bit of effort in the steel industries now to harness the heat which otherwise is being lost to the environment following the melting operations of steel, and tundish cover, more and more tundish cover, ladle cover, etc. have been used in order to minimize heat losses so that the power consumption in electric arc furnace can be smaller. The processing time thus will also be smaller. So, we can transfer molten metal. So, no steel plant which is producing quality steel will do open stream casting. Okay? So, everybody will be using a ladle shroud. It is almost a standard artifact in the steel industry and is very vital during the transfer operation. It is coupling with the collector nozzle, the refractory quality of the refractory, because molten metal is accelerating and flowing down at large speed. So, therefore, there is a good chance of erosion of refractories, and these refractories have to be good, otherwise steel can be contaminated with what is known as exogenous inclusion, which I have already said. So, now when you have opened the lid, this is called ladle opening. So, once you brought that ladle from after the VD, okay, holding period is over, you will lift the ladle and bring it onto the turret just above the continuous casting tundish. At that particular moment, what happens? The tundish is hot, it is preheated. In steel making, in no reactors molten metal is going to be transferred which is cold. Okay? Otherwise, there will be premature solidification of molten steel. So, it is also at 1100 the tundish is fired before, so they know at what time the ladle will be coming, and accordingly the tundish is going to be preheated. So, the ladle is going to be opened into the tundish, and as I have indicated that a tundish basically is a buffer vessel. Okay? It is equipped with or fitted with a number of strands, and these strands, to the best of my knowledge, I know that they are either minimum number is 1. So, one inlet and one outlet, which you call as one strand, and the maximum I know is a 16 strand tundish operating somewhere in China. In India, I think the maximum number of strand in a billet caster. As the section size will become smaller and smaller to maintain the same throughput rate, because the plant productivity has to be maintained. So, we will require more number of strands. So, billets are small cross section, slabs are large cross section. So, when we are talking about slab casting plants by the by are also known as flat product plants. On the other hand, billet and blooms, okay, they are known as the long product steel plants. So, when we are casting billets or blooms, because their section size is small, mass per unit length is small. So, you will require more number of strands to sustain the same throughput rate. On the other hand, if you are talking of slab, okay, in that case, because the slab per unit length, the mass of steel is larger, so you will require less number of strands. So, the tundish can be equipped with a number of strands through which molten metal will be feeding into the continuous casting mold. So, what I have shown here is the continuous casting mold. This is a schematic representation, and here also the transfer from the tundish into the mold will take place under protective environment, and this device is not called ladle shroud, but it is called a submerged entry nozzle, SEN, in continuous casting. So, it is submerged under molten steel here, and the solidified, we will discuss this. You must understand that when I talked about conversion process mentioned, the conversion process in the steel industry are two types of conversion: ingot casting and continuous casting. Ingot casting is a batch process, and continuous casting is that you take one ladle, bring another ladle, the same tundish stays and the casting continues, and it can continue for 16 hits, 20 hits, 20 ladles it can take at a stretch, and the casting can go for 2 days. For example, on the other hand, ingot casting is a batch process where you have number of molds into which molten metal, one mold at a time, or maybe a cluster of mold, 8 molds or something like that. So, you have, they are arranged in something like, so we can have 4 ingot molds. This is my ladle, okay, and there are runners here. We can have 8 molds also, and they are always arranged like this. So, because we want the resistance in the path of the fluid flow to be identical for each of the mold, otherwise all mold will not be filling at the same rate. Now, imagine a plant which produces, which is huge blast furnace. I was talking about 3.5 million tons of steel, a 7 million ton steel plant, 2 blast furnaces, 3.5 million ton each, and 10,000 tons per day is the hot metal production, 10,000 tons, okay, roughly about that value, to quote, you know, what do you call, very nice looking figure. So 3.57 million ton plant, 2 blast furnace, each blast furnace is 3.5 million ton, and therefore in 365 days, okay, we have, you know, per day 1 blast furnace is producing. And suppose this much of steel is being produced in the plant, therefore on a daily basis. Now if you imagine, if you have 1 ingot mold weighs about 10 ton, then you require how many number of ingot molds? 1000 ingot molds you will be requiring. This maintaining of this large number of molds is going to be a cumbersome exercise, you know, lifting the mold, taking them out, and they can be occupying lot of space. So the high rate of production of a modern steel making plants cannot be satisfied by the batch process like ingot casting, and we require now a conversion process which is far more faster and far more efficient in converting liquid steel into solidified product. But we must understand that in the process of conversion, we should not do things so hurriedly that the products become defective. That is a big challenge, and that we will be addressing when we talk about the casting processes. So therefore, you know, and here you can imagine that, as I said, that if you are operating not even at 1 ton or 8 tons, take a value like 5 tons per minute. If you take 5 tons per minute, that means in every hour you are casting 300 tons. Okay? So that means 24 hours, 7,000 tons a daily. That means if you have 2 casting machines, you will be able to cast, you know, the machines will be idle for some amount of time. So 2 casters will be able to, you know, handle 10,000 tons a day, absolutely no problem itself. Okay? So therefore, you know, in large steel plants, particularly those producing continuous, you know, plain carbon steel as well as special steels, I mean, people will never go for ingot casting. Ingot casting is used today only for niche products. Okay? For very specific kind of products, only people will like to have ingot casting process. The quality of steel, of course, becomes much better. Okay? The chances of defects in ingot casting are also much smaller, but technologically it is not viable. From the profitability point of view, it is not viable. From the logistics point of view, it is not viable. So most of the plants will. And this is a typical continuous casting setup, that you will have a ladle sitting above the tundish, which will be sitting above the mold. So the ladle will be somewhere about 3 floors up. Okay? And this, the discharge of the continuous casting, this is the product of the continuous casting machine, that will be at the ground level, okay, where you will be, you know, chopping this off, because this one length, if you do not cut it somewhere, then because it produces continuously, so you can imagine that it could have a length of about 30 meters or 40 meters or something like that. So you will be chopping them off at regular intervals. So you will have a first slab, second slab, third slab, and so on and so forth as a function of time, or first bloom, second bloom, third bloom, and so on and so forth. So therefore, when a ladle is brought to the turret, the ladle is opened into a tundish. Okay? The tundish is empty, but it is hot, and there is a chance that this tundish, if you have not taken care of, what it is filled with? It is filled with atmospheric air. So in an initial tundish which is empty, when molten metal is discharged and starts to flow like this, it is creating a scenario like an open air, you know, casting process, because it is filled with atmospheric air, and therefore there is going to be huge amount of atmospheric air which will be getting into the tundish, and as a result of which molten steel is going to be continuously dissolving oxygen and entraining oxygen from the tundish environment itself, and this phenomena will go on till we find that the shroud tip is submerged, and then of course there is no more oxygen entrainment. These arrows which I have shown will now be not. So this is now the shroud tip is submerged. Okay? So therefore the molten metal does not see the atmospheric oxygen. It is only here that, you know. So the turbulent mixing of air and steel will no more take place, but of course it is true that we have, you know, this this is the interface at which the atmospheric, the air contained in the tundish will come in contact. So, as the tundish metal is filled, we add what is known as a tundish powder, and this tundish powder are going to protect. The tundish powder has two different purposes. It will immediately produce a cover, preventing any further contact with the atmospheric air. Okay. So, these powders have two different characteristics. The powder which is in contact with the steel, which is containing less silica, and that which is above this powder we have more silica. Less silica may be about 8% silica or so on and so forth, and this could be about 45–50% silica. So, we have two different kinds of powders, and this powder, I will say not the yellow one, okay. This is basically called the tundish covering compound. This is the insulator basically. Okay. On the other hand, this less silica powder, I think Spartek is the name of one such powder which is used as a trademark. Okay. So, in continuous casting process. So, this powder basically it melts and it forms what is known as a inclusion absorbing slag. So, this is the liquid slag. This powder will give rise to tundish powder will give rise to liquid slag, and this is going to be the covering agent. So, that is going to now prevent any further atmospheric contact with the molten metal till the flow rates are adjusted in such a way that, and that is why I say that initially, so we want the shroud tip to be submerged as early as possible. So, initially we want lot of material from ladle to go, because there is going to be, in that case, the quicker the tundish shroud tip submerges into the molten metal, less is going to be the air steel interactions. So, if there is significant amount of air steel interactions, the steel will become dirty, because dissolved aluminum will react with oxygen in that turbulent mixing zones, and as a result of which the first bloom which comes out, or the first slab which comes out, are never sold to they are not called the prime products, because they will be the result of reoxidation in the tundish itself. To circumvent these problems, to salvage a part of the first bloom or first slab, what people these days do, they have a tundish cover, and then before the casting starts, they will flush tundish with inert gas like argon. Argon is heavier, so the argon, if you flush argon 10–15 minutes, then bulk of the oxygen or the air can be driven out, and then you can create a scenario as if the tundish, even though the shroud tip is not submerged, it will take some time to get submerged, but the shroud molten metal discharged from the shroud will see an environment in the tundish which is no more containing atmospheric oxygen, but containing an inert gas like argon, and thus reducing the extent of oxygen absorption, nitrogen absorption in the tundish. Okay. So, therefore, flushing of tundish prior to the beginning of the casting, okay, is very important exercise, and it is also important that the tundish is operated with a reasonably tight cover. And then of course, these powders are to be added. The lower powder, which is liquid, which remains in the liquid state, will absorb the inclusions, because the inclusions are always rising up, and we will see that in a minute. Okay. And then the top part is going to be insulated, because we do not want molten steel to lose its heat within the tundish to a significant level. So, flow rate can be controlled, okay? And then eventually what happens if you draw the flow rate versus time from ladle, and you will see that the flow rate from the ladle to the tundish goes something like this. Initially you have a 0, and then you can have a very large flow rate, and then gradually the flow rate could be decreased, and then it is going to be bringing to a steady state. So, this is a high flow rate, and then you go even higher than this is the steady state. So, this is Q tundish, volumetric flow rate from volumetric flow rate from ladle, and this is as a function of time, and this is the period when we say that steady state condition has been reached. So, nothing is changing in tundish, Okay? The flow is stabilized, the bath depth is stabilized, tundish weight is stabilized, everything is stabilized. So, beyond this point nothing changes, but initially this throttling is very important, and this is done deliberately, that if you want to use more than the steady state flow rate, our objective is only to submerge the shroud tip as early as possible. The tundish, molten metal enters into tundish, and as you can see, as I have drawn here, as if the tundish does not contain anything, it appears to be a simple kind of a box type reactor, but it is not like that. The tundishes have many internal furnitures which we call as flow control devices. It is also true, coming back to this point, that when the ladle, the steady state condition is going to be disturbed when the ladle will be exhausted. Okay? That period I have not shown here. So, if the ladle is moved, in that case what happens is the flow rate can really, from the ladle flow rate will go down directly to 0, because there is no inflow from the ladle. So, and then what happens is that you will bring in another ladle, and then again the same thing is going to go. Okay? But in the process what happens is there is going to be a fluctuation of the steady state bath depth level. So, volumetric flow rate from the, if you draw the bath depth, for example, the bath depth would be, I would say, would be monotonically increasing initially at a large high speed, and then the bath depth will remain constant. And beyond this point the bath depth will go down a little bit, and then again go up, and then again become like this. So, this is the period of ladle changeover. So, what is this? This is the bath depth, variation of bath depth as a function of time. And what is this? This is the mass flow rate from ladle, flow rate from. So, this is where the ladle is removed, ladle removed. If you do only one casting with one ladle and you say the casting is over, I do not want to use it. So, it is called a single head casting. On the other hand, if you use the same casting, because you are making huge, your customer has come to you, said that I require 5,000 tons of given grade of carbon steel. So, obviously, you will not be having one single ladle, you will be having maybe 25 ladles. So, if you cast one after the another ladle, that is called in the industry as sequence casting operation, same grade of steel being cast continuously. When the requirement of the volume requirement is large, but volume requirement is small, you have only one hit, single hit casting as opposed to lead hit casting, as opposed to sequence casting. So, now this tundish, as I have indicated, shown here, it possibly tells you that there is nothing inside, but there is going to be, there are tundish furnitures, and these furnitures are called flow control devices. When the tundish is operated under steady state, there is a parameter called nominal residence time, nominal residence time, and that residence time is basically the steady state tundish volume, steady state V sub tundish at steady state, okay, divided by volumetric flow rate from ladle, okay, Q in at steady state. Meters cube per second, this is meter cube. So, if you divide one by the other, then you get parameter in seconds, and that is the nominal residence time. This nominal residence time will vary depending on whether you are having a bloom casting tundish or a slab casting tundish. Also, the tundishes have different designs. It is not a one single design. I will draw the top section of the tundish. One section of the tundish really looks something like this. This is one type of tundish, okay, and then this. So, we can have, this is the ladle, and this could be your a 3-strand tundish. On the other hand, we can have a box type tundish, the top view, where we can have, this is the inlet and these are the 2-strand tundish. On the other hand, you can have single strand tundish, you have this is. So, cross represents where the shroud is entering into the tundish, and then here also you have different kinds of delta shaped, T shaped tundish is also there, H shaped tundish is also there. This is also another type of tundish which is mostly symmetrical. So, you can say various types of tundish designs are there. So, their surface area, the volumes are going to be different. So, thus their nominal residence time, and also surface area to volume is also going to be different. So, therefore, we can understand that there is going to be considerable amount of variation in terms of heat losses from the tundish, because typically you may note that bloom casting tundishes are of this particular variety. On the other hand, billet casting tundish and slab casting tundishes are of this particular variety. So, this is slab and billet, this is slab and billet, and most of the bloom casting tundishes have, they are 3 strand or 4 strand tundishes, and they are basically delta shaped or T shaped tundish and so on. There are, these are popular shapes, that is what I wanted to tell you. There are many other shapes also which are possible. So, the nominal residence time differs in the tundish. What is the value of nominal residence time? For example, if you go to a slab casting tundish can have a volume, 37 tons could be the capacity of the tundish, and then you could be casting about 3 tons per minute, and then a slab casting which will approximately tell you that 12 minutes. If you go to a bloom casting tundish, the bloom casting tundish could have something like depending on the conditions, it can have about 8 tons, or it can have about 16 tons. So, the maximum casting could be about 1 ton per minute, that is the casting, and if you divide, then you can have 8 to about 16 minutes. So, 12 to about 15 minutes I would say for slab casting tundish, and 8 to about 16 minutes, but the surface area to bloom volume ratio is significantly larger in these cases than it is in this particular cases. Regardless of the fact that these tundishes are going to be all covered, there is going to be more or pronounced drop in temperature. Pronounced drop means we are not talking about 100-degree drops, we are talking about 5 degree, 4 degree and something like that, okay, and that is enormous when you say the mass flow rate multiplied with the specific heat of steel, which is about 700 kg joules per kg, okay, and mass flow rate is about 1 ton. So, it is a huge value, even though delta T could be only about 4 degree or so. So, on the other hand, in the case of slab casting tundishes, okay, and these tundishes, when you have, for example, as I have indicated, could have about 16 strands, you can imagine that the flow here is entering from one ladle, and this is, we have 8 strands on this side and 8 strands on that side. This farthest strand possibly does not see any motion of steel except for the drainage action that the molten metal is going out, okay. It is the churning action, the high turbulence region is restricted mostly in and around the shroud region itself, but far away from the ladle shroud region elsewhere the bath is pretty much stagnant. I would not say stagnant, but very slowly moving, and slowly moving regions, if you all know that they are desirable for inclusion flotation, because inclusions are very small. If you have a strong convection current, inclusions will be taken away along with the fluid. So, a quiescent kind of a slowly moving tundish is desirable, particularly for the removal of inclusions. That molten steel spends some amount of time which is equivalent to the nominal residence time. Of course, all elements do not spend the same amount of time, some spend little longer or some spend. So, there is a residence time distribution, we will not talk anything about that. It is sufficient for us to note that the tundish, the fluid will spend some amount of time in tundish. So, therefore, the issue is, can we exploit that residence time for which the fluid is going to spend in the tundish, and further improve the cleanliness of steel, or further help steel floats inclusions which can be absorbed by the slag which is in the liquid state, and this composition has been engineered in such a way that it becomes liquid and it is friendly to the rising inclusions, so that it can capture the inclusions without much problem. Okay? So, therefore, it is important for us that we try to exploit this scenario, that tundish spend some amount of time and we create a quiescent kind of a flow scenario. So, that is why, because we have a very large turbulence available in this particular region because of the high flow rate of molten steel. So, there could be quite a bit of slag metal mixing here also, okay? And that is why you will see that in a bare tundish means the tundish contains no flow control devices or no flow modifiers, molten metal will really be poured in, and we will invariably have what is known as a pouring box or a turbo stop immediately below. This helps to contain the molten metal, this helps to protect the bottom of the tundish, because molten metal is coming impinging directly onto the base of the tundish. So, that can damage the refractories if you are thinking of producing a sequence casting with long sequence. So, you require something to protect, and also this additional surface area will give resistance to the flow. The flow pattern is going to be changed and the turbulence is going to be damped, because the fluid has now will flow like this, and then it is going to go out, and in the process of that the fluid is going to come in contact with solid. So, the solid liquid frictional force is going to slow down the liquid, and as a result of which the intensity of turbulence which is a function of the flow velocities is going to be significantly dampened. So, there is a designs here available, the surfaces are serrated surfaces to create more amount of, just like golf balls are never what do you call smooth, they are they have to create the surface area. They are, of course, the objective is different, they want to destabilize the turbulence boundary layer. In this particular case, you simply have more amount of surfaces created by producing serrated designs on the surface, so that the surface area for frictional forces between the solid and the liquid becomes larger, resulting in slowing of the fluid, and as a result the slag metal mixing etc. is going to be smaller in this particular region itself. So, most of the tundishes are going to be operated with a pouring box. This is called a pouring box. Imagine if you do not have a pouring box, then what happens? Molten metal is going to impinge onto the tundish base and then flow radially outward along the base, and that will lead to significant amount of what is known as a short circuiting flow. That means the fluid is not spending much time, it is coming in, and you can imagine that if the box is not there, then the fluid strikes here and then it takes to go straight away out, and so without spending much time the fluid will go out, and that phenomena is termed as short circuiting, and that is perhaps not desirable for producing clean steel. Okay? So, therefore, there are many reasons that we will have indeed a turbo stop which is operated. Also, in addition to turbo stops, many tundishes are operated with what is known as a dam, and this dam deflects the flow and lets it to the upward direction, because otherwise what will happen? If the inclusion is at this level, it has to climb through a height of this, but the dam will create a surface directed flow. The turbo stop will create a surface directed flow, and this surface directed flows in tundish is going to help removal of inclusions. So, therefore, a bare tundish is going to be rarely used in the industry. Okay? The tundish will be fitted with what is known as flow friendly artifacts, refractory artifacts, which are made of castables or high alumina bricks, which can sustain the flow pressures and does not undergo much degradation in terms of erosion etc., contaminating liquid steel. So, therefore, we will have a turbo stop, we may have a dam, and there is some tundishes are operated to separate the slag out, what is known as weir, and we have seen that weir in the context of blast furnace runners, where the slag is separated from the metal. Okay? So, dam and weir and turbo stops, these are very common artifacts, refractory artifacts or refractory flow mode control devices used in tundishes in order to create favorable flow conditions leading to. So, there is no scope for doing any chemical adjustment here. We will not do sulfur control or anything. Steel composition is made. The last effort is that we think 10 minutes time it is going to 12 minutes time it is going to spend here. Can we further remove the inclusions or not? Can we further improve the cleanliness or not? That is the whole objective of treating or looking at tundish from that particular perspective. So, if you can create a surface directed flow, if you can prevent short circuiting, in that case what happens is, and if you have in general a quiescent kind of a flow, not too strong a current, a good absorbing slag, fluid slag which will absorb the inclusions, in that case significant amount of improvement in cleanliness can be obtained. You must understand that the slag will contain SiO2, okay, and that SiO2 can undergo reaction also. This is in slag and this is in dissolved aluminum, is in molten metal, and as a result of which Al2O3 can get generated. This is, and that is the reason why we require the slag which is in contact with molten metal, particularly in the casting of aluminum keel steel, to contain less amount of silica. Otherwise, this reaction will take place in the forward direction, because this is feasible under steel making conditions or the conditions prevalent in tundish, generating more amount of aluminum inclusions, and as a result of which what happens, the steel will get contaminated with. This is called reoxidation via the top layer, and if tundish has oxygen already present, tundish is not flushed, it is not covered, then we will call that it is the atmospheric air reoxidation in tundish. So, reoxidation in tundish is a very big challenge. Okay? We must understand that we have spent so much of an effort. The best quality of steel is sitting in the ladle, okay, in terms of its cleanliness. I want to preserve that quality, and I must ensure that during the transfer processes via a tundish, the quality of steel does not undergo any deterioration, and that is a big challenge to the steel makers, and therefore, this reaction must be minimized at any cost in the tundish. So is the ingression of atmospheric air, okay, through the shout joint, as well as air steel mixing in the tundish, and this must be stopped at any case. You must understand that, as I have indicated, by monitoring dissolved aluminum or soluble aluminum at here, soluble aluminum in tundish and soluble aluminum in the final product, you will be able to quantify that to what extent reoxidation has taken place. If no reoxidation has taken place, the dissolved aluminum level in tundish, in ladle, in tundish, and in the final product will remain more or less same, barring the first slab. I am not going to consider the first slab or the first bloom, because the first bloom is always going to be downgraded. It is not a prime bloom. It may contain the starting of the casting. The beginning is not a steady state, so it is not a smooth condition. So the first slab or bloom produced may not be of correct quality. So second bloom onwards, if you analyze and if you find that the dissolved aluminum content here, dissolved aluminum at the steady state and dissolved aluminum in the tundish are essentially same, then we can say that there is no reoxidation which has taken place in tundish. I have 5 more minutes of discussion on tundish metallurgy, and then I will move on to the last topic, that is the continuous and ingot casting or the conversion processes.